Hello everyone, welcome to the lecture Energy Geophysics. In lecture 3, we're going to continue talking about the elastic waves in the continuum, which is the contents of the chapter 6. In previous lecture, in lecture 2, we've talked about the basic concept of the wave equations and the propagation in the bounded media. And today we're going to cover the sections 6.7 to the final sections here. First, we'll talk about the attenuation. So here we're going to relax one of the assumptions, that's medium homogeneity. So this means that we're going to consider the dispersion. So whenever there's a dispersion, you have energy attenuation. So the wave will, the amplitude of the wave will decrease as shown in this figure as it travels through the media. And this is called the intrinsic material losses in plane wave. So you can think of, imagine this kind of a cylindrical specimen, and if you hit it, when you excite with a steel ball, the wave will go back and forth, right? Will travel through the media and bounce back, and then also the bounce back and forth, and it's gonna die out because of the material loss, material damping. So we're gonna talk about that in this chapter. So basically we assume it's a low loss phenomenon, and the propagation of small strain waves in particulate materials, and the elastic modulus can be replaced by a complex modulus. So it was just the elastic modulus when we don't consider the dispersion or the attenuation, but when you start accounting for the attenuation, now we are introducing the complex modulus. So the P wave equation becomes a little bit modified. So before, this was the basic equation when we assumed the homogeneous material without dispersion. But as we are assuming now the dispersive material, so we are going to introduce the complex modulus instead of just just real value of it. So the particle motion will be also expressed with this complex propagation constant gamma asterisk here. And when you the definition of this gamma asterisk is kappa minus I alpha, and here the alpha is called attenuation coefficient. So before there was no alpha, right? Alpha was 0, and now the alpha is not 0. So that the wave attenuates as it propagates. So the alpha is in spatial scale as it propagates through the distance over x distance. The amplitude decreases exponentially, exponential to minus a times alpha times x, and kappa is the wave number. So the particle motion equations will be modified a little bit with this alpha, and you can see this represents the amplitude degradation over the oscillations. And you can simplify the equation like this. So then wave velocity is again the omega over gamma asterisk. So before, the wave velocity is omega over kappa, and that's because it was from the lambda f, the wavelength times frequency, because the kappa is 2 pi over lambda. So then you end up with this equation. So then instead of this kappa, now we are replacing it with the gamma asterisk. Then this will be the expression for the PA velocity in complex form. Okay, so the real phase velocity is the real value of a reciprocal of the VP asterisk. And then you can derive this one. And when you simplify it, by assuming the tangent delta is much smaller than 1, then this becomes square root of m prime over rho. So here, this term represents the dispersion term, and tangent delta is the term to indicate the material loss, the energy loss, or the attenuation, you can call it. And attenuation part is the imaginary part of the 1 over Vp, and when you simplify it, alpha is omega tangent delta over 2 Vp. So you can see that the this alpha coefficient, how much it decreases over the distance, is function of the frequency and velocity and tangent delta. And tangent delta is what we call the material intrinsic damping, the attenuation. So in summary, Vp, the PA velocity will be square root of the modulus over density, and the alpha, the attenuation coefficient, will be omega tangent delta over 2 Vp. This intrinsic material attenuation implies dispersion and phase shift. That means that as the wave propagates, it will shift it a little bit by this much, and whenever you have a dispersion. And the higher frequency attenuates faster. Oh, let me use than the low frequency wave. And the peak of the spectrum shifts to lower frequency with distance. So that's because the high frequency dies faster than the low frequency content. Shape of the propagating wavelet becomes wider with distance. So if you have a, let's say that in the frequency content it was like this, but as it propagates, it becomes like this. So the frequency also gets bigger, the wider. And then how do we estimate this material loss? To quantify the intrinsic material loss, we can use the resonance or free vibration decay or transient pulse and the quasi-static loading. Damping coefficient, we use damping coefficient quite a lot, and the D, the ratio between the D is defined as the ratio between system damping and the critical damping, and D is C over CC, and the C is 2 times square root of Km. So it's a simple, it's for the simple single degree of freedom system. And here C is the damping coefficient, and K is the stiffness, and the M is the material mass. And if you can obtain the hysteresis, the curve, stress strain curve with the hysteresis, like this kind of a loop, then the energy disappeared or energy dissipation can be estimated using the area calculation. So then d is delta w over 4 pi w. Okay. Yes. Here the S is the stored energy that's hashed with the this triangle, and the one with the blue one is the lost energy. And simpler way is to calculate the logarithmic decrement over the wave number. So here the natural logarithm of the ratio between two successive amplitudes in a free vibration system. So for example, if you have this kind of a system, and when it oscillates going up and down, right, and you can record the displacement, the vertical displacement which is going up and down, and it's gonna die over time, right? So then if you pick up this A and this amplitude after one cycle, maybe you can use also this one, A double prime. Then by looking at the logarithmic decrement, we can compute the delta here. Or looking at the average one, you can compare the A and A double prime and use the number 2, n of 2 here. Quality factor is also another term for to describe the intrinsic material loss in terms of the real and the imaginary components of the modulus m. And we said before the m is the complex number, and that's defined as the complex number like this with the m prime and m double prime, and m double prime over m prime is defined as the quality factor, and that's 2 times the damping coefficient. The loss angle delta is the phase angle between the stress and the strain. Also, this one is the term to get the to describe the attenuation, and the delta here is called the loss angle. So it's just the there are numerous different ways to describe the attenuation, but it all indicates the same material loss, delta, or d, or alpha t, or alpha x, or 1 over q, or tangent delta. They are all the same. Huh? Or here also the alpha here. Okay, let's go back here. Skin depth is the penetration of a plane wave into a material that causes decaying amplitude by 1 over e. So this means that if this is the 1, then this will be 1 over e. Or if this is the a, then a times 1 over e. And looking at here, then this is the x, the distance over that amplitude decrement. So then skin depth. So the skin depth tells you how far it can travel before the amplitude reduces by factor of 1 over e. So then you can solve this equation, right? Then here a naught epsilon alpha x 1 over e, and e minus alpha x is 1 over e is e over minus 1, so the minus alpha x is minus L, so the x is 1 over alpha. So skin depth, the distance that the wave can travel, is 1 over alpha. So if you know the alpha, which is the attenuation coefficient, then you can estimate the skin depth. Okay. So these are the relationships between the attenuation parameters. And there are numerous coefficients. So then total attenuation includes three types of attenuation. One is geometric spreading, and second is the material loss, and third is apparent attenuation. We're going to talk about this one by one. So let's talk about the geometric spreading first. Geometric spreading is a decrease in wave amplitude with distance due to an increase in the size of the surface front. So you can think of like dynamite buried in here in a certain depth, and when it explodes, it will create a huge energy and also the wave, and that wave front will propagate, and if we say that all the energy at this front surface or surface front is the same or preserved in here, then the energy at a certain per area will decrease due to this geometric spreading. So wave amplitude is proportional to the square root of the energy per unit area, and the amplitude here, A and A prime, A double prime over R, R prime, or R double prime can be expressed like this. A2 over A1 is R1 over R2, and this we go eta exponent. For the spherical front, this eta is 1 because the area is the 4 times pi times r squared, and the energy is inversely proportional to a square root of r. And cylindrical front is like you can think of like this kind of a disk, and r is here, and the h is a certain distance, a certain thickness that doesn't change with r. So then the power exponent will be 0.5. For the plane wave, like the wave in a rod, it doesn't experience any geometric spreading, so the eta power exponent will be 0. So as we've seen in the lecture 2, when you solve the equation for the plane wave, there is no geometric spreading. There's only the material. Here it doesn't have a dispersion. So, but in spherical wave, there's 1 over r, a term here, because the eta is 1 in this equation. So it travels, and the amplitude will decrease over a distance. And the second one, so the first one was the geometric spreading, and the second attenuation component is the material loss that we call the intrinsic damping or intrinsic attenuation. If material losses are modeled as an exponential decay, the amplitude at location 2 related to the amplitude at location 1 as A2 is A1 times E minus alpha R2 minus R1. So for example, if we have this kind of a bar and we are measuring the amplitude when you hit the one end of the bar with this steel ball, then it's gonna have, this will pick up the signal like this, and also this will pick up the signal in a kind of delayed manner but smaller amplitude. Yes. So, and by looking at the amplitude A1 and A2, we can identify the damping coefficient or the attenuation coefficient of the material. And this is the equation for that. The last one is the apparent attenuation, and this is caused by the discontinuity. So you remember that you have two different material with different impedance. here Z1 and Z2, and when there's incident wave, there's a reflective wave and there's a transmission wave, right? So then here you have ACC1 and here ACC, oh sorry, the 1 and ACC2. Then amplitude measured at ACC1 is A1 and amplitude measured at ACC2 will be A2. Then the transmission coefficient will determine the amplitude at the second material after the discontinuity. So the total attenuation, the contributions of geometric spreading, material losses, and the apparent attenuation can be all considered together. So the amplitude decrease can be described by this equation, R2 over R1 to the geometric spreading coefficient or power exponent. And here exponential function with the alpha, and t is for the transmission coefficient. There's an example that we're gonna solve together in the class, or you can go ahead and solve it for yourself. Okay, in the section 6.9, we're gonna talk about the phase velocity and group velocity. Whenever you have a dispersion, it means that the velocity changes with frequency. If the phase, certain velocity at a given frequency is called the phase velocity. So phase velocity, you can express the phase velocity is like etc. or the 100 meter per second for the frequency of like 10 hertz. This phase velocity can change with frequency. So if the phase velocity decreases with frequency, and it's called a normal dispersion. If the phase velocity increases with frequency, it's called anomalous dispersion. Waves are rarely perfectly monochromatic, but instead have a finite bandwidth. So when you stump media, then it will create the wave, but that wave does not have only one frequency. It will contain a band of frequency. So if the band is, say, maybe 10 hertz to 100 hertz, then your frequency spectrum will look like this, with 10, with 100 here. So energy is spread over a certain frequency range here. So then each frequency will have its own phase velocity. So the bandwidth centered around some mean frequency. Also, you can also define the mean frequency. Frequency in the wave packet is assumed only slightly different. The example is here. You have one single frequency which is 60 hertz, and the other one, the other wave has the 55 hertz. And when you combine together, it becomes like this. So this is the first one with the 60 hertz, and this one with the 55 hertz. And when you combine and superpose it both, and wave becomes like this, because some case it cancels each other. Right. So you can see it kind of oscillate, and it's called the undulation. And in each packet, and this much of the wave is called wave packet. And inside one packet, you have several oscillations. So superposition of the two equal amplitude traveling disturbances is like this, and using some trigonometric relation, there are modulation term and carrier term. So here these are the modulation, and in each modulation, which is the low frequency term, inside you have a higher frequency term. So the modulation results in the building up of groups with amplitude c, which move along with the group velocity. So group velocity moves as a packet. So you can pick up the what you call the first arrival, and if you pick up the way each frequency like this, for example, here that we have a two frequency, right? And this arrival time is the combination of the 55 and 65 Hertz, but this one is just the 60 Hertz frequency content. So if you follow the peak one, the peak value of each of these higher frequency contents, then it will tell you the phase velocity. So here phase velocity and group velocity. So the velocity of the modulation wave, I said that this is the Vm and carrier is Vc. Carrier means that it's a higher frequency content. Then here when the group velocity is the limit of the modulation velocity. So as the wave number goes to 0, this becomes d omega over d kappa. So here you can see that group velocity is the tangent of a certain wave number or at certain frequency, while the phase velocity is just the secant value to that point. So phase velocity is omega over kappa, and group velocity is round omega over round k, omega round k. So when a wave contains a narrow band of frequency, or if it is not strongly dispersive, its propagation can be adequately described by the corresponding group velocity. In this case, group velocity is the velocity of the energy propagation. So this, when we measure the wave velocity using band element, and we are picking up the first arrival, and that's group velocity. And it assumes that the wave velocity doesn't change that much with the frequency. However, the propagation velocity of the wide band disturbance in a dispersive medium cannot be characterized by any single group velocity, because the velocity will change significantly with the frequency. So it could be phase velocity can increase like this, or it could be decrease like this. Summary: the phase velocity, the velocity at which the wave front of a pure frequency tone travel, and group velocity is the velocity of the wave packets, which are made up of a range of spectral components travel. So the concept is there, the wave velocity and the phase velocity, the group velocity and the phase velocity. Then, based on the equation that we saw and we learned in the last lecture, we can compare the different propagation modes. Here, VL is the velocity, longitudinal wave velocity with the Poisson's effect, and Vs is the shear wave velocity, and Vp is PA velocity. And Poisson's ratio correlates the VL and the Vs like this, also Vp and Vs. And velocity ratio, the Vp over Vs, so it can be expressed as a function of Poisson's ratio. And the Rayleigh wave, or the surface wave, also can be expressed as a function of Poisson's ratio and the shear wave velocity. So if we compare it for a range of Poisson's ratio, when we have Poisson's ratio 0, then it will cancel out. So it's gonna be a square root of 2. So it will be 1.4 around that. And Rayleigh wave over shear wave can also be, it's gonna be 0, 0, so that it's 0.874. So you can see as Poisson's ratio increases from 0 to 0.5, as 0 Poisson's ratio, it's about 0.874. When the shear velocity is 1. When Poisson's ratio is 0.5, then almost they're same or close to each other, 95% of the shear wave velocity. And Rayleigh wave also approached to about like 93% when the Poisson ratio is 0.3, which is the kind of medium value that we use frequently for the soil. So the ratio of the VP and VS depends on the Poisson ratio. In homogeneous half space, Rayleigh wave velocity is constant and slightly less than the shear velocity. In layered half space, the Rayleigh wave is dispersive. The velocity is a function of frequency or wavelength. So you can read it through with the textbook. When we compare the damping ratio or the damping coefficient for different propagation modes, the relationship between damping coefficient is different propagation modes when the loss assumption, and then this kind of a relationship can be built. So P wave motion and longitudinal wave motion with the Poisson effect, which means that you allow the lateral deformation, and QS is one of QS is the shear wave attenuation. One of the following relations must be true, which is QS is largest and QL is the next and QP is the smallest when the VP over VS is low. And when the VP over VS is high, which is a fully saturated case, then QP is the largest and QS is the smallest. And attenuation of the Rayleigh waves is related to the attenuation of the body wave. So you can compute based on the velocity and QS and QP. Then you can estimate the Rayleigh wave attenuation, QR. As I said before, the 1 over Q is the same with 2 times damping ratio. So now we're gonna talk about relaxing the isotropic assumption. So when we relax this assumption, now we are considering anisotropy. You can read it through. And this is based on the modulus of mechanics. And when stress is in 2 dimensions, there are 3 components: sigma x and sigma z and the tau zx, which is the shear. So in 2D, you have normal stress, 2 normal stress, and 1 shear stress. And if the shear stress is 0, then it's the principal plane. So principal stress is just 2. In 3 dimensions, you have 6 stresses component because these are symmetric. Right? Sigma x, y, z, and tau x, y, tau z, x, and tau y, z. And for the principal planes, principal stresses are just the normal stress without the shear stress. So sigma 1, sigma 2, and sigma 3. And if we think about the stress-strain relation or constitutive relation, then this will be the elasticity theory, and sigma is modulus times strain. And here, if it's truly anisotropic, the modulus will have 81 components because the stress is 9 components and the strain is 9 components. Because the matrix is symmetric, in reality, you have a 36 6 stress and 6 strain, so that the matrix will be 6 by 6 stiffness matrix. And here the bottom one, below the diagonal term, will be the same with the upper diagonal term, so it's symmetric. So we need the 21 components to fully describe the anisotropy. But sometimes in soil we often encounter the layered media. So typically we saw orthotropic material. So orthotropic material has at least 2 orthogonal planes of symmetry, where the material properties are independent of direction within each plane. So here means that this direction and this direction, you have the same property, but to the other direction here in z direction, it's not symmetric. That means that it's orthotropic. Or you can think of this kind of a tree trunk, and in tree trunk, in radial direction, it's gonna be the same. In transverse direction, also it's the same, but in z direction, also z direction you don't have the anisotropy, but this one and this one can be different, right? So then also this kind of a material is called the orthotropic too. And so it requires a 9 independent variable, 3 elastic moduli, 3 shear moduli, and 3 Poisson's ratio. And cross anisotropy is the special class of the orthotropic material. And so this is the same, just like I said before. In this direction, one plane is the same, the isotropic, but in z direction is anisotropic. So then now you need less variables. And then this is the summary table, and what we can see is the how they propagate through this kind of a cross anisotropic material. So we can assume that wave velocity increases over distance. Maybe here the confining stress is much less than the case here, so the wave velocity will increase like this. Let's say that it's Vs with the depths. Then, but in this direction and this direction, the wave velocity can remain same. So this is cross anisotropic problem, and 5 independent constants are required like this, and pure shear mode, quasi shear mode, and quasi longitudinal mode, and theta is the angle between the normal and the wave front, and the z-axis symmetric. So if we go over here, the stiffness is controlled by the effective stress. Stiffness increases with depth. Furthermore, due to the frictional resistance, stress on anisotropy should be expected. And gradual changes in stiffness cause continuous refraction and lead to curved rays. So this follows the Fermat's principle. The ray travels on the path that minimizes the travel time between 2 points. So when you think about the wave propagation in 2 different media, let's say that ray goes in, and we have a V1 and V2. If the V2 is much higher, then it's gonna go over this path, curved path, to get to the receiver from the source, and it's called a ray. So in a gradually heterogeneous weakly anisotropic medium, let's say that the the velocity z direction to this direction increases with the depth, and c is the coefficient indicating the ratio between the vertical direction velocity over horizontal direction velocity, and v theta is the velocity at a certain incident angle theta. Then equation of the ray path can be driven as shown in this box. Actually, you can derive it. This is the homework, and then if you use this equation to plot it, here source is here, xs comma zs, and the receiver is here, and you can think of the receiver at different depths, 10, 0, 10, 2, minus 2, 10, minus 4, 10, minus 6, right? That's the receiver coordinate, and source coordinate is 0, 0, right? So you can put the numbers here. And then if as the A, let's say that let's look at the red one. When the A is 90 meter per second. So what's the A? So here Vg A plus Vc, and B is 5 seconds, and C is 1. C is 1, so Vg equals to Vx, isotropic medium. So then it will show like this kind of a curved ray, and this is the path that the wave arrived the earliest. If we change the parameter here while keeping the A and B the same, we are just increasing the C to 1.1. Now that what Vz and Vc, so the vertical C is Vz over Vx is 1.1, so that the vertical velocity is higher than the horizontal velocity. So then it will show like more curved shape, so it will go down deeper because the vertical velocity is higher, and then it kind of curve and to get to the receiver point. Okay, so this kind of shows that the how cross anisotropy affects the ray path and arrival time too. And we can also relax the linear elasticity when you have a large amplitude excitation. So you can think of the sonic shock. So if the variation of the stiffness with the strain is positive, that means the stiffness increases with the strain. So if you push the material, like for example the air, if we compress the air really high with a higher force, because of the large strain, it will compress and the stiffness will increase. And then the first portion of the cycle affects the following the strain. So now it becomes more stiffer. So you have a very distorted wave like this. So you can see that the stiffening the shape of the front of the pulse, stretching the rarefaction cycle. So this is the final comments and summary, and you can read it through, and end of the lecture 3. Thank you for listening.